The Earth's magnetic field is an invisible but crucial shield that protects life on our planet from harmful cosmic and solar radiation. Generated by the movement of molten iron in the Earth's outer core, this magnetic field is not static. Over geological timescales, it undergoes dramatic changes, including full pole reversals where the magnetic north and south poles swap places. This phenomenon, known as a geomagnetic reversal, raises intriguing and sometimes alarming questions. Chief among them, could a geomagnetic shockwave or pole flip disrupt everything? To answer that, let's unpack what a pole flip actually is, what a geomagnetic shockwave might entail, and what the real-world consequences could be. Earth's magnetic poles have reversed many times in the past. These reversals are recorded in the alignment of magnetic minerals and ancient lava flows and oceanic crust, which preserve a fossil of the direction of Earth's magnetic field when they formed. On average, reversals have occurred every 200,000 to 300,000 years, though the timing is irregular. The last full reversal, known as the Brunhes-Matuyama reversal, happened about 780,000 years ago. Despite what Hollywood might suggest, pole flips don't happen overnight. Instead, they unfold over thousands of years. During this transitional period, the field can become disorganized and significantly weaker, potentially allowing more cosmic and solar radiation to reach Earth's surface. The term geomagnetic shockwave isn't a standard scientific term, but it's often used informally to describe a sudden, intense disturbance in Earth's magnetosphere. These can be triggered by solar events such as coronal mass ejections, massive bursts of solar plasma and magnetic fields from the sun that collide with Earth's magnetosphere. A powerful CME can compress the magnetic field, inducing electric currents in power lines, pipelines, and satellites. This has happened before. The Carrington event of 1859 is a prime example. Telegraph systems failed, and auroras were seen as far south as the Caribbean. If a similar event occurred today, it could cause widespread technological disruption. While not directly related to a pole flip, such a shockwave could become more disruptive if Earth's magnetic field were already weakened during a reversal period. So, what happens during a geomagnetic pole reversal, and could it really disrupt everything? During a reversal, the Earth's magnetic field doesn't disappear, but becomes significantly weaker and more complex. Multiple north and south poles can emerge simultaneously, and the overall field strength could drop to as low as 10% of its current strength. A weaker field allows more solar and cosmic radiation to penetrate the atmosphere. While Earth's thick atmosphere still offers substantial protection, the increased radiation could affect high-altitude flights, satellites, and astronauts. There is little evidence to suggest that humans on the surface would be directly harmed, but frequent flyers and those living at high altitudes might experience increased radiation exposure. The magnetic field plays a critical role in shielding satellites and enabling navigation systems. Increased radiation could damage or destroy satellite electronics, reduce operational lifespans, and degrade communication and GPS services. Polar flight routes, which already require careful monitoring for solar storms, could become riskier or unviable. Ground-induced currents from geomagnetic storms could overload transformers and grid infrastructure, leading to blackouts. Many modern navigation systems, including military and aviation, still rely in part on magnetic compasses. A shifting or unstable magnetic field could lead to navigational errors if not recalibrated regularly. Birds, whales, and other animals use Earth's magnetic field to migrate. A rapidly changing field could confuse migratory routes, although there is evidence animals can adapt over time. there's limited evidence suggesting that geomagnetic reversals directly affect climate. Some theories propose that a weakened magnetic field could slightly alter atmospheric dynamics, but climate is influenced far more by greenhouse gases, solar cycles, and ocean currents. The phrase "disrupt everything" is understandably dramatic but overly broad. Unlikely. While disruptions to technology could be severe, particularly in communications, navigation, and power systems, they would be manageable with preparation and adaptive infrastructure. No evidence supports this. Humans have survived multiple past reversals without technology. Our current technological dependency is the key vulnerability, not our biology. Some scientists speculate we may be in the early stages of a reversal, as Earth's magnetic field has weakened about 9% in the past 170 years. One area of interest is the South Atlantic anomaly, a region where the magnetic field is particularly weak. However, these anomalies may not indicate an imminent reversal. Reversals are unpredictable, and the field may simply strengthen again. Designing satellites to withstand higher radiation levels. Implementing transformers and systems resistant to geomagnetically induced currents. Continued investment in space weather prediction and magnetic field observation. Developing alternative navigation methods, including satellite-based and inertial systems. A geomagnetic pole flip is a complex and slow-moving process that could indeed have disruptive effects, particularly in our technology-dependent world. However, it's not the doomsday scenario that some media portray. Life has survived dozens of reversals before, and humanity, with foresight and planning, can mitigate the risks. While the idea of a geomagnetic shockwave accompanying a pole flip makes for compelling science fiction, in reality, the transition would more likely be a long and challenging adjustment, not a sudden global catastrophe. It may disrupt a great deal, but it certainly won't disrupt everything.